Okay, so last time we discussed on Coleman superspace. And sigma 1 also then Coleman superspace. Equals 1. So let's see sigma 1 was. We saw that the corresponding supercharges that plays the role of the Dirac operator. Coupled to various forms possible. Yeah. And so, as we discussed in the first lectures, the most interesting for symmetry actually is at least n equals 2, and n equals 1 is upgraded to n equals 2, and there is this Z2 grading on the representation space. So today we'll explicitly describe n equals 2. So the models that we'll write will explicitly have n equals 2 supersymmetry. Here equals 2 space. So n equals 2 superspace. So there's a two real supercharges with anti-commutation relations. Like this. So in principle, it's a super Lie algebra over the real numbers. We can complexify it by even before complexifying, let's just say that the corresponding supergroup, which is the superspace, so this is the supergroup of this corresponding to this supergroup called G super, so this time n equals 2. It has the coordinates t, theta 1, theta 2. So we'll equivalently use complex coordinates, which are theta and theta bar. There are complex combination of these guys. So it's I theta 2. And yeah, like I said, we can complexify the Lie algebra. Then we can equivalently rewrite it as a in terms of the complex supercharges. So from now on, by Q, we will denote complex supercharge. So this is Q1 plus I2, some constant. And then the algebra is Q squared is nilpotent. Squared is 0. This Q bar squared. And anti-commutator Q is Q bar. So Q is normalized, so the anti-commutator is 2H. Then we can consider functions on this superspace or on this supergroup. We can consider left and right vector fields just before. So the left vector fields will corresponding to the Q generators will be the corresponding supercharges in superspace. So these are vector fields in superspace. The vector fields in superspace. U can be written as minus I d over dt plus theta bar d theta, theta bar d over dt. And bar minus I. So this is the bar plus theta. And then you can check that this differential operators, these vector fields, they satisfy this algebra relation, where H is now minus I Notice it's a matter of some technicality that Q bar is not really kind of naively complex conjugate to Q with some signs. This is related to how we interchange fermions under complex conjugation. We swap their positions. Okay, and then there are the right vector fields, which are the superderivatives. Let's write them out. So D over d theta minus I theta bar for dt d bar d over d theta bar d over dt. And again, they satisfy the same commutation relations as the supercharges. So d squared is d bar squared 0, intercommutator d and d bar to h. But the important property is that they anti-commute with the q's. So d with q equals q bar 0. So when constructing superspace actions, we can use those as kind of derivative.
And the same for d bar.
Yeah, plus complex conjugation, yes. Conjugate equations, yes. So the superfields now, so they're functions of this theta bar. So superfields. Let's call it phi 0, 0 plus theta phi 0, 1. Theta bar phi 1, 0 plus theta bar by 1, 1. So these are functions of t. Again, this is all required to be compatible with the grading, with the Grassmann grading. So the grading of phi is equal to grading of phi 0, 0 equal to grading of phi 1, 1 is equal to grading of phi 0, 1 plus 1. 1, 0 plus 1. So so let us make a brief comparison with n equals 1. So when n equals 1, we had this Lie algebra of q squared is h. It can be written in terms of intercommutator and so on. So we want a representation in, so just to recall, we want representation in Z2 graded vector space. So the corresponding irreducible representation is of dimension 2. So where Q is, for example, Q can be written as 0, 1, 1, 0, and minus 1 to the F. So the grading can be written as 1, 0, 0, minus 1. They anti-commute, of course. And the Hamiltonian is just the unit matrix. So this is a representation of the real Lie algebra. So this can be viewed as a representation in R2. And to this representation, there corresponds the corresponding real superfield. We studied before. To this representation, there corresponds the real superfield. This is n equals 1. The field, which has y equals x plus I theta chi, the one that we studied earlier. So notice that without the grading, without the restriction of the grading, we would have a representation of dimension 1, right? We could just have Q equal to 1, H equal to 1, for example. But with the Z2 restriction, it has to be two-dimensional. So what about n equals 2 case? So in n equals 2, we can consider the representation of the complexified Lie algebra. So over C, the dimension of the two graded reducible representation is 2. So, for example, you can take Q1 equals 0, 1, 1, 0. So the compound matrices, right? So there's this one, Q2, this one, minus 1 to the F. Minus 1 to the F is the third compound matrix. So this is the presentation in C2. So this is in C2. We may ask though if this can be as well thought of as a representation in R2. If we can actually represent our real Lie algebra in a real two-dimensional space. So of course, naively, I mean, this is not so because this Q2 is a complex matrix. So in R2, you could take, for example, okay, you could say that Q1 is 0, 1, 1, 0, and Q2 is, for example, 1, 0, 0. So these are real matrices. So this is a representation in R2. But again, if you want a Z2 grading operator, this will be 0 minus I 0. So this is not a real matrix. Again, so not real. we can ask question mark. This is not real. So this is not really a representation in R2. So over the Z2 gradient representation of the real algebra is of dimension 4. So you can represent it in R4. Basically just by promoting these I's to matrices.
So in 3 dimensions also impossible.
Yeah, in 3 dimensions also impossible, yes. Well, I don't really know a proof, but it should be semi-obvious. Well, I mean, you cannot represent the...
Yeah, I mean, what I'm thinking, because you can, SU2, because it is Pauli matrices, you can represent SU2 in all 3.
Yes.
But I mean, you should be careful about grading things, right? I cannot do it.
No, but because if you represent an R3, then the square of each matrix will not be 1, right? Will not be... They will not be equal.
Okay.
They will be like 1, 1, 0, 1, 1, 0, 1, 0, 1.
Okay.
Right? Because yes. We also have, I mean, I don't write here, but we also imply that there is H.
Yes.
The unit matrix here also. But in R4, you can write, so you can write Q's 1 is sigma 1. So 1, 1, 0, and 1, 2. Q2 is 1, 0 times unit matrix. And this guy minus 1 to the f is just 0, 1 minus 1, 0 times 0, 1 minus 1, 0. So we just promote the I to this supersymmetric matrix. Now they all work nicely. They anti-commute and square to the unit matrix. So 4-dimensional. Here we have kind of two types of representations. The one over the real numbers of dimension 4, and one over the complex numbers of. And accordingly, we have two types of superfields that we can use. So first, we have a real. So to this representation, there corresponds a real superfield. Real superfield phi, which is now phi plus theta to the power 1, where now, so these guys are real. Is real. This is complex. This is complex conjugate to it. So this is exactly 4 components, 4 real components. So apart from this real superfield, we also have some complex superfield corresponding to the complex dimensional representation. So it's real superfield, and then we have a complex, what is called chiral superfield. So the point is that if you just take a superfield, complex superfield phi with all independent components, then we have 4 right? We want two components. So there's some condition that we impose on phi so that it would have 2 components. And so the condition, so let's call it Z to kind of to show that it's a complex variable. So this is depends on theta and theta bar. Of course, it also has some expansion in thetas. But now we will impose the condition that d bar of t will be 0. So so this is kind of some kind of analog and superspace of holomorphicity condition. Yes, so that's why we call it chiral is a kind of holomorphic. It's holomorphic. If you could as well say that d of 0, z is 0, then it would be anti-holomorphic or anti. So let us write out this constraint. So if you just differentiate, you write the z field with a generic expansion like that, and then you find that this is z10 minus theta z11 minus I theta z00 dot minus I the theta bar d10 dot. And this is 0. Require this 0. So then we equate the coefficients of various powers of thetas. Yes, so we find that this is 0. This is 0. So z10 is 0. And z11 is minus I 0 dot. That means that if we now substitute this into the expansion of the thetas, right? This I just differentiated the generic field. I just substitute your z's everywhere. Okay, this is a real one, so don't look at this one. But I mean, so that means that z can be written as z0 z00 plus theta 1 time minus I theta bar z0 dot. And it's sometimes more conveniently, this is written as follows, that this is z00 of t minus I theta bar plus theta z01 of t minus I theta bar. So you see what happened here? We just repackaged these two terms as a Taylor expansion that truncates. And in the second term, we just write it kind of to be more symmetric. So say that we can change the time to the shifted time. I see. Yes. I mean, here everything truncates immediately. Here there is one term, which is one extra term, it's this. So we can say that. So the point is that if you recall the expression for d bar, what is d bar? This starts like d over d bar plus something, right? So we want to say that kind of the superfield, chiral superfield, is the one that doesn't depend on theta bar. But of course, it's up to something. So this something is this shift of the time variable. So it depends on theta bar, but only in some combination. And otherwise, it can be solved with just a function of theta. So in other words, it means that z, the function of this shifted time, theta. Right? So it only depends on theta bar in a controlled way. Right? It doesn't introduce new field components in theta bar. So So this is the general chiral superfield. And then equals to, and it has two components, two independent components, Z00, Z01, they're complex, right? And yeah, notice that it has to be complex from perspective of superfields because yeah, let's just make a few comments about this. So yeah, and this the important point why this condition also makes sense is that doesn't introduce new constraints on the superfields, because if you act with d bar, so d bar squared is 0. So some remarks. So the remarks are as follows. So first of all, these chiral fields form an algebra, right? Of complex numbers. Just because d bar of z is still 0. Take an arbitrary polynomial like z, just by Leibniz rule. It's also annihilated by d bar. So second is if z is chiral, then z bar is anti-chiral. This follows from the fact that if you so z is written here. If we write z bar, this is 0 bar plus minus plus z 1 bar theta bar plus I theta bar z0 dot, and therefore d of z bar is I theta bar 0 bar dot minus I bar 0 bar dot. So this is 0. So it's annihilated by d. So in particular, this implies that z has to be complex, because if z is real, so if z real, then it's annihilated by both z is both chiral and anti-chiral, and that means that it's annihilated by the anti-commutator of d bar minus I minus 2I d dot 0. That says that z is a constant, unless you want a constant field, you cannot can have z real. So that's the point with this chirality conditions. The point is that you can you have to impose a closed set of constraints, right? For example, here d bar equals 0, d squared, d bar squared is 0. So there's no further constraints. If we require the d and d bar is 0, then there are additional constraints coming from the commutator. So will be relevant in n equals 4 also. So, then there is also some kind of superspace Poincare lemma. So raise with this new level or with open. No, that's correct. So d bar. So if d bar z is 0, then there is such b that z equals d bar b. So d bar squared is 0. So so kind of homology of d bar is trivial. So let's rule this. So d bar z is 0. So that means right. This implies it just means component wise that so if you take a generic field B, d bar B is B10 theta B11 plus I dot minus I B10 dot. This has to be equal to Z. So it's not be equal to Z, which as we know, kind of from here, is 0, 0, plus theta 0, 1 minus I theta into bar B11 Z 0, 0 dot. Right, so we find that take B10 is Z0, 0, and B11 minus Z0, 1 minus I D0, 0 dot. So the field B derivative is Z. B is B0, 0, theta B0, 1, theta bar C0, 0, minus theta bar B0, 1 plus I. So you see, it's not uniquely determined by Z, right? It has these three components, which are B0, 0, B0, 1. And this comes from the fact that, of course, we can add to B some derivative, right? So we can D of D bar C. This doesn't change. Z because D squared is 0. And so that field C will precisely, we can use it actually to precisely to kill those components to set D0, 0, 0. If you wish, you can do that. So let's precisely the right content. That would be useful in writing operations function of the actions that we will write. And finally, the correspondent is about supersymmetry transformations. So as we recall, this is just the action of the corresponding vector field on this on the superfield. So this is delta z, that is epsilon q, it's epsilon bar q bar acting on z. And this gives minus epsilon z 0, 1 minus bar epsilon bar theta dot minus epsilon theta theta bar 0, 1 dot. So this means that the variations of the components of z are delta 0 z 0 0 is minus pi epsilon z 0 1 z 0 dot. So you see the supercharged Q has parameter epsilon, so this epsilon transformation is nilpotent. Yes, so z00 transformed to z01, and 001 is not transformed under epsilon. Same for epsilon bar, but together they close so that the transformation of this gives the derivative, the original. So, these are the supersymmetry transformations, and the important thing to notice is that again, just like in the case of n equals 1 superfields, the top non-trivial component is shifted by a derivative. Here, the top by top, we mean the one that's not a derivative itself. So these Carl fields have this property that the top component is a derivative itself. But remember, we used this property of shift under derivative to construct actions. Of course, if we take just naively the top component, it's a derivative itself. So it's not an interesting action, it's zero by definition. So we want to take the top component that's not a derivative. So in this case, it will be z01. And it's shifted by derivative. So we can use that to construct action. So this is the top. So in fact, this construction, I don't know exactly the precise way to formulate it. Maybe you can help with it. But I mean, this construction with superspace and imposing constraints is similar to a construction that you have for compact simple groups. So, for example, you can have let's take say a SU2 or whatever G compact simple group. And you can consider the representation of G in L2 of G, right? On space of square integrable functions. And we want to pick out an irreducible representation out of it, right? So so this L2 of G is kind of the analog of superspace. Yeah? So by the Peter-Weil theorem, we decomposed as a sum over all representations of G, all finite dimensional representations as v lambda times v lambda dual. So the left one corresponds to the representation of the left action for the left action. This one corresponds to the representation for the right action. And now, okay, this is not a reducible representation; it's highly reducible. But we want to pick out a single irreducible component. So what we can do is we can impose some constraints on this. Namely, the constraints that we will consider only functions L2 of G that are annihilated by that are highest weight with respect to the right action. So V plus F 0, where V plus are all positive roots. So vector fields vector fields positive roots or negative roots, positive roots of the right action. And by the way, these positive roots, they take values in they are elements of the complexified algebra. So this kind of automatically requires that these L2 of G, these are complex valued functions on G, which is analog of parallel supergroup. That's fine. What I want to say. So F is a complex valued function. That's the integral of G. So if we take this means we take highest weight vector. So that means that in each right representation we take the highest weight vector. So such functions, so the space of such functions, which we call L2 of G 0, let's say. So this has the sum over all lambdas, the lambda times C highest weight vector. So that's already some improvement. And then we can fix impose the condition that these functions also have some fixed value of the Cartan generators, right? So V0F 0 I AF is some weights. We fix the weight actually. Just these are some A1 to rank of G. So these are the weights. So we fix the weight, and by this we pick only one representation with given highest weight. So these are all highest weight representations. We have different highest weights. So this is so to double zero in the space of such guys. This is inside G0.
So V0, it is another vector field.
Yes, A. Yeah, there are A vector fields corresponding to the Cartan of the G, and we require that yes, our functions are eigenvectors of these. And of course, they cannot be arbitrary; they have to be integer, and so the eigenvalue has to be integer and so on, corresponding to the weights. Otherwise, we get 0, right? I mean, empty space. Then this L2. This is not just G0. L2 of G00 will be the lambda, where lambda corresponds to that highest weight, lambda of H. So this is a way to pick out a reducible representation from just functions. Maybe next time we'll discuss a bit about harmonic superspace. It actually kind of uses this version of construction. But here I just want to say that this is kind of similar to what we do with this quadratic constraint, right? We impose the D and D bar should be thought of as the roots of the algebra. So you impose the positive root annihilates the field. And then in principle, to get something irreducible, I guess we need to impose the Cartan value of Cartan. Value of Cartan here would be the value of H. So it's like fixing H. So without, really, when we talk about chiral superfields, we don't impose the value of H because we want our functions to be kind of arbitrary functions of time, right? So I don't really know if in like what's the correct representation theoretic way of saying that. So it's kind of the it's like this L2 G0.
Well, I think because you consider fields, so your fields, they are functions in variable t.
Yes.
So it is not finite dimensional.
Representation, you mean?
So t is like you live in one parameter subgroup. Yes, so t is a parameter you exponentiate.
Yeah.
Oh, I see it.
Yeah.
I see.
Yeah, I mean, if I say that my superfield is is e to the lambda t, or then energy t, then I get this will be a finite dimensional representation, and the theta expansion components will be just the usual doublet. You see, but you know, in mechanics we don't want to assume some.
Yeah, I see. Yeah.
Because usually in the superspace business, people call this a reducible model. But it's a reducible in this sense. It's like a reducible when you fix your energy, then it becomes an irreducible representation of your
irreducible model.
Yes, but I think that's only correct if you fix the value of the energy. See, kind of you see what I mean, right?
Yes. Yeah, I see.
But there's some jargon people call it irreducible in the sense that you cannot also impose additional constraints on it, additional superspace constraints. But I think the correct way to state it is that once you fix the value of the Cartan element, so the energy, it will become just an irreducible representation of your Clifford algebra. That's which is why I have related the real and complex representation the way we did before to superfield. You know, I think that's the precise relation, but usually not spelled out. So that's the best I can make out of it. Okay, let's make a little break and then we discuss the models that we start with such actions. Okay, so let's continue. So now we are done a little bit with some abstract theory. Maybe we come back to it in the context of n equals 4 next time. So the point is that, well, the idea is to impose some on the general complex superfield. You can impose some constraints using these right vector fields, which kind of get as close to the notion of a reducible representation as you can get kind of in this context. So here it's only the only possibility to find this chiral or anti-chiral or real superfield. Of course, real, you can have two real superfields, combine them into a complex superfield. That's level. Now we will speak about the actions or the actual models that you can write with this. So supersymmetric actions. So there are two ways to construct invariant actions here. So the first is as an n equals 1 superspace. So you just take an integral over the superspace. You can also view it as an integral over the supergroup here, of some function called g, related to the group, just some function. So z of z is the bar, possibly dz. D bar is the bar. And if you have real superfields, we can have I d phi, d bar phi, etc. So it can be function of complex real, I mean, with chiral or real superfields. Um, and so yes. So you see, if you take there's some reservation that needs to be made here. So suppose this function g depends only on z, then it's also a chiral superfield, right? Then it's the corresponding contribution. So you have some function f equals z. This will be proportional to minus I df z over dt. This is total derivative, as we discussed before. The top component is a total derivative, so that means that g is defined up to adding holomorphic plus anti-holomorphic function. So g should be a real function, real valued function. G is defined to g plus f of real part of that. As we noticed, the top non-trivial component of the chiral superfield is shifted by derivative. So we can also use that component to construct superfield, right? So what we can do instead of this, we can write an action of the form d theta f of z. If so z kind of doesn't depend on theta bar, but it depends on theta. Yes. So so this is another ingredient for the action. This will be complex now because it's a function of complex holomorphic function of complex variables. Plus complex conjugates. So by complex conjugate, I mean integral over theta bar, f bar, d bar. This will again be a real function. But notice that now f has to be Grassmann odd for this to be Grassmann even. This has to be Grassmann odd. So the general action will have these two terms. Usually, so there is some kind of conflict in the notion of superpotential in general supersymmetric models. Many things are called superpotential, but typically superpotential is something that depends on chiral superfields, usually. So this would be kind of a n equals 2 version of superpotential with this thing. Yeah, this is really confusing because in these models, there's another object that's called superpotential, which is the superpotential we used in the first lecture. It was some bosonic function, Grassmann even function. So that one enters here as follows. So maybe it's a bit. Maybe just think of this f as some kind of Grassmann version of superpotential. Because now we'll also have another one that's bosonic. So anyway, the next is two types of models with n equals 2 supersymmetry. So models, sigma models. supersymmetry. These are called 2A model and 2B model. So now is the field content. So in the 2A model, we have real superfields. Real superfields. So in particular, this includes Witten model that we studied before. Witten model. And this 2B model, it includes chiral superfields. So chiral always come together with antichiral, which are their complex conjugates. So chiral superfields. So let's start from the 2A model. Or 2A model. So here we have real superfields, X1. I relabel them from phi to x's because their top components will be, their leading component will be bosonic field X. So these are meant to be real coordinates on our target space. The coordinates. XM. And the action that we will write as follows. So G is the metric now. This W is also called superpotential, but this should be it should be understood that this is a real function, real value function. So this has the real superpotential. So this is the superpotential in the sense that we used in the first lectures. We had some real function, which was then converted to potential. And we will see that it precisely leads to that kind of model, which is the reason why this function W appeared. So from the point of view of supersymmetry, it's more natural to have this W function rather than the bosonic potential. It can be recovered from here. So you see it's a kind of potential in superspace. Okay, so there's a metric on them. Yeah, one could consider more general stuff. For example, one could add some skew symmetric parts like B, DAB, DXA, DXB, plus complex conjugate. And this skew symmetric, possible antisymmetric, but we will not do so now. But I'm saying that they're different generalizations. And so now we'll recover the Witten model as we discussed it earlier from this formulation. So this is an expression in n equals 2 superspace, right? Remember, before we had n equals 1. So to recover the old formulation, we will precisely do the reduction from n equals 2 to n equals 1. So in n equals 2, we have to, let's recall that we also have real superspace variables, theta 1, theta 2. And we want to reduce it to theta 1. Right, this is the reduction. So how do we do the reduction? Well, so we have the integral here over 2 thetas, right? So we have d2 theta is what? Is just the same as differentiation. Equal 0, as we discussed before. So that means, yes, and integral over d theta 1 we want to arrive at is that the derivative with respect to d1, theta 1. So what we're doing now is we want to say that our superspace Lagrangian in n equals 1 superspace is just the derivative the Lagrangian in n equals 2 superspace at theta 2 equals 0. Instead of doing, so to get the usual Platonic Lagrangian, we have to differentiate twice. But to get the n equals 1 superspace, we just differentiate once with respect to the variable that we want to get rid of. But we should recall, so the derivatives that stand here are this chiral derivatives, complex derivatives. So d is d1 plus I d2. Accordingly, d bar is d1 minus d2. So in n equals 1 superspace, d1 will be just the derivative of n equals 1, the super derivative of n equals 1 superspace. So we want to get rid of d2, all right? So d1 will be just the derivative of n equals 1 superspace, and we will call it curly d, just the super derivative of n equals 1 superspace. So the point is that the so our real superfield, our real n equals 2 superfield x, each x will split into two real n equals 1 superfield, which are xa, that's theta 2 equals 0, and d2. Equals 0 that we will call psi a. A because it's the Grassmann odd. So you see, it's like coefficients of Taylor expansion is corresponding variable, and they are independent. So because of course we have four variables in the real n equals 2 superfield, but here we have four variables, and here in each we have two variables, two fields. Yeah. So let us compute the first term in the action. What we need to do is, so first term is d2, and compute the derivative. Actually, from the term. So, first we for example, let us differentiate the so have Yeah. So plus so let's start with the two acting on d bar xb. So similar term. And then when we differentiate the metric. So here I've written the explicit differentiation just to enhance an understanding of how this is done in practice. So here I open this derivative d as d1 plus id2, extend this as d1 plus id2, and then I act with d2, right? d2. So there is a term. The second term is d2 squared, and the first term I anti-commute d2 with d1, and I replace d1 with the curly d, which will be just my definition. So now what I need to do, I need to say that this d2xa is psi a, the new field. Then this guy is just xa dot, right? Derivative, because yeah. And for example, here d2xb is psi b. And I mean, the derivatives, d1 derivatives just stay as derivative. Then equals one superspace. And then there is a completely similar term where d2 acts on the d bar, which I don't write out. And then there's this additional term, which, okay, this is also psi c, right? And this guy has to be expanded as d xa plus I psi a. And similarly for this. So this is d xb minus I psi b. This is how it all decomposed into n equals one superfields. And then you open the brackets. What you get eventually is the following term. So this is so you get I dxb, which is now you see that this nicely combines. So this psi terms combines with this into a, like we discussed, the psi is a section of a tangent bundle. So this is a connection in the tangent bundle, Christoffel connection. So becomes VAB XA dot B plus my nabla psi A, psi B. Where it's kind of pullback of Christoffel connection to the super space. And you see, we recognize the three parts. So in our previous lectures, we considered just this case where the target space was a flat space, right? And we had those additional real fermionic fields there. As we saw, it's necessary to formulate the potential term in the model. So that you see how they arise from this n equals 2 construction. So in n equals 2 construction, this x and psi sit in the one real superfield, n equals 2 superfield. And this is how it's decomposed back into n equals 1. So let's finally, let's see the potential term. So it also gives the right result. So the potential term easier. So basically, you just say take a derivative of w of x. This is d. This is psi a. So if you remember when we considered, so we considered the Witten model with in flat space, so just model one-dimensional particle and potential. So the model from lectures. And M is just R, dimensional space. And in this case, so we had the superspace Lagrangian is just this 2 x dot dx plus 2I, maybe wrestling the 2 plus I deep psi, psi deep psi, I plus W prime x times psi. This is the, so we cover the Lagrangian. So yes, this is the, so that model is a special case of this two-way model. And maybe it's worth also noting that in this, as we discussed last time, in n equals 1 superspace, our superphase space was like we discussed. So in n equals 1, kind of superphase space was star plus IT of n. So it's a direct sum of vector bundles, cotangent bundle, bosonic cotangent bundle, and fermionic tangent bundle. But actually, in the simplest Lagrangian like this, in component form, in component, if you see what the superspace is, superphase space is, you can go to component form, and you find that the leading term, well, this is what? This is x dot squared over 2 plus I psi bar psi dot. Maybe psi is not good. Let's call it V2 bar. V2 dot. So here we have a complex Fermi. Where does it come from? Well, it comes from the top leading component of this real psi field, and the second component of X. So they together they come symmetrically somehow, although it doesn't look like this here, and they combine into a complex. So actually here the superphase space is like I said back then, is a T star of phi T by T of M, which is T star plus pi T pi T star. Yeah. So you have a fermion and a section of the tangent bundle, a dual fermion section of the tangent bundle. So fermions are doubled. So, and in higher end models, there will be some more complicated. So they always live in some bundle over your target space. Okay, and so next time already, I think we will study the 2B model. So so the 2B model would be a model of with chiral fields. So this is so sigma model with chiral fields. So there will be some M will be necessarily a complex manifold. So this model works for any manifold. The 2A model, this will have a complex manifold with chiral superfields that play the role of complex coordinates. The n, so it's the complex dimension of M is n. The model will be given by an action kind of similar to the one we had before. G model. And here there are two ingredients. Notice that these fields are chiral, so that means d bar dA0, so it only makes sense to write like this. And so we'll see it also gives some sigma model with some additional terms. So the superpotential the real superpotential that we had last time is replaced by this, what is called a Kähler potential. We'll see that it leads to an additional gauge field on our manifold next time. But it's important to bear in mind that this notion of Kähler and superpotential have slightly different meaning in various models. So, for example, in this model, the scalar potential will actually define just a gauge field of some connection. on the target space and some line bundle on the target space. But in n equals 4 models, the Kähler potential will define the metric in the target space. Also, the super potential that we discussed in the 2A model is a real valued function. But we'll see that in n equals 4 theory, super potential is a complex holomorphic function. So, so this terminology, unfortunately, a little bit, yeah, sometimes misleading. Hope it will not mislead the listeners. So anyway, that's it for today. I'll see you on Tuesday.